Hi guys, welcome to the third section, Linear Regression. In this section, we will start with compensating factors in machine learning models. Next, we will see simple linear regression from first principles and wine quality data. After that, we will see multi-linear regression. Finally, we will see linear regression model that is ridge and lasso regression. Now, we move on to the first video of this section that deals with compensating factors in machine learning. In this video, we're going to take a look at assumptions of linear regression and steps of linear regression modeling. Compensating factors in machine learning models to equate statistical diagnostics is explained with the example of a beam being supported by two supports. If one of the supports doesn't exist, the beam will eventually fall down by moving out of balance. Here, we are comparing statistical modeling and machine learning methodologies. The two-point validation is performed on the statistical modeling methodology on training data using overall model accuracy and individual parameters significance test. Due to the fact that either linear or logistic regression has less variance by shape of the model itself, hence there would be very little chance of it working worse on unseen data. Hence, during deployment, these models do not incur too many deviated results. In the machine learning space, models have a high degree of flexibility, which can change from simple to highly complex. Statistical diagnostics on individual variables are not performed in machine learning. Hence, it is important to ensure the robustness to avoid overfitting of the models, which will ensure its usability during the implementation phase to ensure correct usage on unseen data. In machine learning, data will be split into three parts. The first part is trained data, that is 50%. Next is the validation data, that is 25%. Last is the testing data, that is 25%. Machine learning models should be developed on training data, and its hyperparameters should be tuned based on validation data to ensure the two-point validation equivalence. This way, the robustness of models is ensured without diagnostics performed at an individual variable level. Before diving deep into comparisons between both streams, we will start understanding the fundamentals of each model individually. Let us start with linear regression. Linear regression has these assumptions, failing which the linear regression model does not hold true. First assumption is the dependent variable should be a linear combination of independent variables. Second assumption is the no autocorrelation in error terms. Next assumption is errors should have zero mean and be normally distributed. After that, the assumption says no or little multi-collinearity. Last assumption is error terms should be homoscedastic. Let's start detailed explanation of the first assumption, that is dependent variable should be a linear combination of independent variables. In simple words, it says y should be a linear combination of x variables. In the given quotation, x2 has raised to the power of 2. The equation is still holding the assumption of a linear combination of variables. Let's diagnose it. Look into residual plots of residual versus independent variables. We will include polynomial terms and see any decrease in residual values, as polynomial terms may capture more signals from the data in case simple linear models do not capture them. The graph simply shows the presence of non-linearity. After increasing the power of the polynomial value, now the errors simply look like white noise. Next assumption says no autocorrelation in error terms, that is presence of correlation in error terms penalized model accuracy. Durbin-Watson's D tests the null hypothesis that the residuals are not linearly autocorrelated. While D can lie between 0 and 4, if D is approximately to 2 indicates no autocorrelation. If D is greater than 0 and less than 2, it implies positive autocorrelation, and D is greater than 2 and less than 4, it indicates negative autocorrelation. Another assumption says error should have zero mean and be normally distributed. This assumption indicates that errors should have zero mean for the model to create an unbiased estimate. Plotting the errors will show the distribution of errors, whereas if error terms are not normally distributed, it implies confidence intervals will become too wide or narrow, which leads to difficulty in estimating coefficients based on minimization of least squares. Let's have a look at the QQ plot. It is evident that the first chart shows errors are normally distributed, as the residuals do not seem to be deviating much compared with the diagonal alike line. It is evident that the first chart shows errors are normally distributed, as the residuals do not seem to be deviating much compared with the diagonal like line, whereas in the right-hand chart, it is clearly showing that errors are not normally distributed. In these scenarios, we need to reevaluate the variables by taking log transformations and so on to make residuals look as they do on the left-hand chart. Next assumption says that no or little multi-collinearity. Multi-collinearity is the case in which independent variables are correlated with each other. This situation creates unstable models by inflating the magnitude of coefficients or estimates. It also becomes difficult to determine which variable is contributing to predict the response variable. VIF is calculated for each independent variable by calculating the r-squared value with respect to all other independent variables and tries to eliminate which variable has the highest VIF value one by one. This is the VIF formula. If VIF is less than equal to 4, suggests no multi-collinearity. In banking scenarios, people use VIF less than equal to 2 also. The last assumption says errors should be homoscedastic. Errors should have constant variance with respect to the independent variable, which leads to impractically wide or narrow confidence intervals for estimates, which degrades the model's performance. One reason for not holding homoscedasticity is due to the presence of outliers in the data, which drags the model fit toward them with higher weights. Now, look at the residual versus dependent variables plot. If any pattern of cone or divergence does exist, it indicates the errors do not have constant variance, which impacts its predictions. Let's see the steps are applied in linear regression modeling in industry. The first step is missing value and outlier treatment. Second step is correlation check of independent variables. Next step is train and test random classification. After that is fit the model on trained data. The last step is evaluate model on test data. In this video, we've learned compensating factors in machine learning models.